Good afternoon, everyone. Just on vacation here in the biggest city in Canada, Toronto. We got the skyscraper, the CN Tower in the background. This is definitely not my setup right now. I'm on a laptop in a basement, but we're going to jump into using environmental variables to get past a small buffer. This is just another vanilla buffer overflow, but it just covers the topic of using environmental variables, which sit above the stack in memory, but we can access those within each program. It is specific to each terminal, but let's jump into it. Enough words. Let's get into our working files. So I'm going to cd to my desktop, cd to day 2, ls-l. And first things first, this is the program we are going to exploit. And I'll just show you, it has a very small buffer 8. Now our shellcode alone that we used in the other videos is 35 bytes. That's a pretty small shellcode. So there would be no way, even though this is vulnerable with stir copy, there's no way that we could put our shellcode in there. So we work around it. We have these things called environmental variables. So these here are all different paths and stuff used by this terminal itself. So one thing you got to be careful of is the environmental variable is only stored in one terminal. So if you go over and try to call it in another, it's not going to work. So first things first, we will build our shellcode. And our shellcode, first off, we need to have, Python-C, print. The first things first, I want to put in about 200 nops. Now nops just provide a place for the program to hit soft landing before it hits our shellcode. Every time the program runs, it could be 10 bytes off here, 10 bytes off there. So that's why we use nops. There are ways to go about not using it, and I'll show you those later. But this is just so we can get used to some basics here. So X90, I want 200 of those. And then I'm going to add in, let's open up another terminal, new terminal, get to our working files. And let's cat shellcode.py. And this is just a basic bin.sh shellcode that I made for this class. And I plan on doing some lessons on shellcoding in the very near future. So here we go. So we have 200 nops, and now the environmental variable is going to have our shellcode after those 200 nops. Perfect. So there we go. Okay, so let's have a look and make sure our shellcode is up there. And as I said, the environmental variables sit above the stack in memory, but we can get inside our program and actually track this down and use it. So it's really cool. So there's our shellcode. I will demonstrate to you though. Let's open up this terminal here, and as we have a look up through, the shellcode is not in this. It's terminal specific, okay? So don't try to call it, everyone has that problem when they start off. So it's only in that terminal. Okay, so we have our shellcode and our nops made. So let's get into the meat and potatoes of crafting our exploit. Let's open up Tiny in our GDB, disassemble the main function. And as you can see, it's 0x20 right here, subtract it for the stack. So that's 32. So we do 32 divided by 4. That's 8 words. The stack is 8 words. So then I'm going to display, let's do 20 words from the stack pointer. Whoops, you got to spell it right. L-A-Y, there we go. I'm also going to set a breakpoint right before the stir copy here. And let's breakpoint at the stir copy. So now I'm going to run it with an input of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's put 12 A's in and we'll have a look at what we need to do to overwrite the EBP and the return address. Return address is going to be a jump to our environmental variables, and we'll track that down in just a sec. But let's get into the basic exploit skeleton, we'll call it. Okay, so you can see our inputs copied in here, 4, 8, 12 bytes of A's. A is 4-1, capital A is 4-1. So let's print where our EBP is. It's at D8. So there's D0, 3, 7, 8. So we need 4, 8, 12, 16, 20 A's. And then, of course, this right here next to the EBP is always the return address. And we confirm that it returns the libc main. And there you go. So we need 4, 8, 12, 16, 20 A's, and then I'm going to put 4 B's. And now we can start crafting our exploit. Okay, so that entered. So I'm going to run this time with Python, because we're cool like that. Python-C, oops, C, print. Let's do some A's again. A times 20, and then I want to add 4 B's to overwrite the 4 bytes of return address. And this is just crafting a skeleton of our exploit. And let's hit next instruction. And as you can see, our A's fill up the stack and the buffer, or the base pointer, and then our B's cover our return address. So this is where we need to put our jump into in our environmental variables. So where are our environmental variables? Well, we can do examine. Let's do 75 strings from ESP plus 0x, let's say 250. So we're going up hex 250 from the ESP. And as you can see, we start to get into the environmental variables here. So where is my shellcode? My shellcode is right here. You can see shellcode 220 repeats 190 times. Okay, so let's grab this and copy. So we can examine, let's say 75, examine 75 words a hex from that address of our shellcode in the environmental variables. And as you can see, here's all our NOPs that we put in, and then our shellcode starts right here. This is our shellcode. So, okay, so what we do, we jump somewhere into the middle of our NOPs, because if you go towards the edge on the top, sometimes that little variation can bump your landing off and it won't work. So copy that. That's going to be our new jump address. I'm going to open a new terminal and just put this in here, just in case we lose it here. Okay, so that's our new jump address. So now that I've shown you how to find environmental variables, and as you can see, we got a segmentation fault. Perfect. Let's continue out of that. So next I'm going to run the program and put a $, Python-C, and print. Now we needed 24 bytes to overwrite our return address. What I'm going to do this time, print, is use my address, a whole bunch. I'm going to times it by, so 4, 8, 12, 16, 20, 24. So we should times it by 6, because it's 4 bytes each. And let's see how that works. This might be the full extent. Let's see. So 80F3. So 80F3 FF BF. So that's our jump address. And of course it's backwards, written in little Indian convention. Okay. So let's run our program. Let's have a look. So we're at our breakpoint before stir copy. Let's see what it looks like copied in. And we got BFFF F380. Let's make sure that's the same. BFFF F380. Perfect. So let's look at where our base pointer is. And it's at C8. So that's that one right here. So our base pointer is overwritten, our full stack's overwritten, and our return address right here is overwritten. So it's going to jump to our environmental variables right in the middle of those NOPs. It's going to hit the NOPs, then run down and trigger our shell. So we should get a shell from this. So let's continue. And boom, process is executing a new program, bin dash. Now, why bin dash is a lower level shell? Because it's a lower level program and we can only get access of what the program has. So we got a lower level shell. We can do some Linux privilege escalation here and take over the system. So that is how you use environmental variables in basic stack exploitation. I hope you guys enjoyed it. I really did. I'm a little under the weather. I'm on vacation, but I've been practicing this stuff every day. So I hope to have a video out soon on bypassing stack cookies, which is another fun video coming up. I hope you guys enjoyed. If you did, share it, like it, and I will talk to you guys in the very near future. Love you guys. Bye.